And the next speaker, well, we have already met him. He's Patrick Lehmann with PLC2. He's the head of system engineering, as well as vice chair of the VHDL analysis and standardization group. He's a computer scientist, developing FPGA-based system, as well as an active contributor to many of the open source tools that we all use, like OSVVM, GHDL, and as well as developer and maintainer of the PoC-Library, which he will guide us through today. Thank you.
Thank you for the introduction. Okay. Is it loud enough? Okay. Yeah, thank you for the introduction. Yeah, as you said, my name is Patrick Lehmann from PLC2. We have seen each other already. So this time it's not about the company, it's about open source and a project I'm involved in since many years from my time at the university. They had an internal IP core called, or IP core library called the PoC-Library, which stands not for proof of concept. That's unfortunate that everyone is using this. It's PILE, of course, and it's a free and open source VHDL IP core library. I want to talk a little bit about the history of PoC, so that you get a basic understanding where we are coming from as a library, what are our goals, what we have inside of the PoC library, what is then done or what has been done in version 2.0 when we released it last year, what have we done in between until this year, and what is coming next with version 3 that we are releasing at FPGA conference in 1 month. So preparation is ongoing. As I said, an overview of the IP course, what's inside, that you have a general introduction. If you want to go more into details, then please contact me. We can speak outside, or we also have recorded sessions at the PLC2 training site, which are free to see again. It's also on YouTube. So there we have more deep dive introductions. I also want to focus on AXI4. This is one of the main additions that PLC2 delivered. The AXI4 infrastructure that is now in the PoC library. Okay, so let's talk a little bit about the background. It's coming from the university where I studied, which is TU Dresden. 2 colleagues, Thomas B. Preusser and Martin Zabel, started there as PhD candidates, and they wrote IP cores. We had the problems that many students were changing FPGA boards, not just between Xilinx devices, also with Altera devices, and the idea was, can we write IP cores in a way that when there is a new master student coming or a new PhD student coming and he needs a bigger board and we need to rip it out of the hands of a bachelor student, that he's not starting from scratch again. So that was one of the basic ideas, how to write IP cores for like Ethernet that's on the boards, UARTs, but also abstraction layers like the OC RAM, so the on-block or on-chip RAM. How can we abstract it? Everything was then put on GitHub, and which is now underneath the VHDL namespace on GitHub. So originally we started in 2007, so it's quite old. It was internal to the university, and it was then transitioned around 2010 to a library, so that every IP core is based on a lower level IP core and everything makes sense. It's not just a collection of IP cores, it's really a library, which is essential when you want to use it. In 2015, we started then to open source it with the Apache 2 license. That's our understanding of using IP cores. Could have been also MIT license or BSD license. We decided for permissive license, in this case Apache 2. We didn't want to go with the LGPL license like others are doing it because there's a licensing problem. We can talk about this outside, what are problems with LGPL and using this with VHDL or Verilog code. There has been further development inside of PLC2. So when I joined the company, the library was used, heavily used in project work, in consultancy work and so on, but the company was not so happy about releasing it directly. So we had some internal convincing ongoing, and finally in 2025 we started to release these internal IP cores. Now you can imagine, after so many years, the code base has diverged a little bit from what is on GitHub, and we have lots of fun in our evenings bringing the internal code base in a way that we can release it on GitHub, which is now getting easier and easier, the more releases we had. And we have a plan within the company to release more and more IP cores. Okay, as I said, we have a permissive license, which is based on Apache 2. This allows you also to use the library in closed source applications, whatever it is. If this is defense, medical, trains, whatever, no problem. You just need to name our libraries. That's the PoC libraries inside. That's the code you're using is underneath Apache 2 license. That's it. The documentation has a similar license, which is Creative Commons with naming the authors. We use a lot of VHDL 2008 inside as far as it's supported by the tools. So we are also stressing the tools as best as we can and as much as it's supported. Maybe you have seen certain LinkedIn posts from my side complaining about Vivado support. Yeah, I got some knock on the head from my company. But on the other side, I have now good contact with AMD, and we are solving problems in the tools. And I think with the next release, you will get a major benefit from Vivado 2026.1. I cannot talk about what it is, but it will be a huge change for you all. They are also integrating VHDL 2019 features into the tool. What I learned from my new colleagues and corporations that I have there, it has been all the time in there, but not documented. And if you look into the user guide 901, you will find new tables of documented features for VHDL 2008 and 2019, which is quite impressive. And as far as I understood, there will be an update again when the next version is coming out. So stay tuned for available VHDL features. Okay, we standardize our interfaces that are inside of the library. Mainly it's then based on AXI family. It is now quite available. When we started the library, the AXI family was not available for free use. It was bound to devices that are using the ARM instruction set, so you cannot use it everywhere. Nowadays, ARM has changed the license, and we are shifting step by step more to the AMBA protocol family. All our IP cores can be configured. You can configure features, algorithms, resource utilization, and pipelining stages or timing. And it's automatically transparent to the selected device. So usually you set up your chip name inside of the library, and then the library is deciding what is the best implementation that's available. We have usually generic implementations, but we also have specialized implementations for Altera devices, for Xilinx devices, and yeah, depending on what we need to do, sometimes generic description is good enough. Okay, in the title, it's also saying we are independent. So what does it mean now to be independent? We are independent of the vendor we are supporting. As I said, Altera, Lattice, AMD devices. We are independent of the target implementation, can be also an ASIC implementation. So there has been tests in the past with using these IP cores also for ASIC development. Not in the recent time, but I'm looking into some support or tools that I can prove it again that they are still working with ASICs. We are toolchain independent also then for simulators, and the next one is operating systems. So as long as it's supported on the matching platforms, we are also trying to support all operating systems. Okay, as I said, PoC version 2.0 was somehow a restart. So for this, we forked the project under GitHub VHDL/PoC. We made some intermediate enhancement releases with version 1.3 and 1.4. So these were preparations. And now we have version 2.3 released since a few days. We activated CI/CD with GitHub Actions. Simulations are running there with VHDL and NVC. And we are using OSVVM as a simulation framework with matching test reporting. The documentation is published also on GitHub pages, so vhdl.github.io/PoC. And no existing code base was degraded when we did the upgrade to version 2.0. All existing test benches need to be converted. So we had an old style of testing at the university. Somehow from me and another colleague, our own invention, not so very good. You cannot compete with existing frameworks, independent if this is a VUnit, a UVVM, or OSVVM. You cannot keep up with these verification frameworks, so don't try your own implementation. It's way too big to do it yourself. So we decided to go with OSVVM, in our case, as a verification framework. And all abstraction layers that are inside of the library are working as they were before. As I said, we had support for multiple tools, and it's now the goal from our side to test this again. So to test with a not so well-known tools, also broadly used tools, what we can say it's working with Vivado, with Rivera Pro, with QuestaSim, with VHDL and NVC. So this is our main test base, and now we are trying to expand it also to Lattice, to Quartus, and so on. We also got contributions with test cases, so we found someone who is willing in writing OSVVM test cases just for fun, so we got more and more test cases converted. And the scripting that's inside of the PoC-Library was Python-based, called IPCMI, IP Core Management Infrastructure. This will be replaced long-term with EDA Square. That's another project from my side, working long-term on it to replace the scripting and to get everything nice and shiny. Okay, so what did we do? We kicked out ISE support. I think it's now, when was the last release? 2013. 13 years later, I think it's time to get rid of some old friends. That means example projects, memory configurations, constraint files, and so on, we kicked out. We also had the idea some very long time ago to have submodules inside of our code base for UVVM, VUnit, and CocoaTV. We also throw them out, and we are focusing now on OSVVM, not meaning which one is better or not. It's what we need inside, and we don't want to be a collector of all kinds of different open source frameworks. We did many bug fixes, and we moved the synchronizers that were previously located under poc.misc.sync directly under the head namespace, which is poc.sync, because we figured out somehow that synchronizers are very important. When you study at university and you ask your colleagues, synchronizers, who needs them? It's always working, right? And then you have real-time, real projects, and you figure out they're really important, and they shouldn't be in a sub-namespace. Okay, so talking about what's inside, we have utilities. Like helper functions is simulation. That's a function that can figure out if your tool is running, or your VHDL language, when you execute it, is it running inside of a simulator, or is it running inside of synthesis? And with this one, you can switch some constants inside. Let's imagine you have a stopwatch. You want to simulate what is 1 second. Do you really need to wait for 100 billion clock cycles or just 10? Yeah, you can switch it on demand. I think every library somehow has a logarithm 2 function to figure out how many bits we need. So it's also inside here. We have conversions between 1 hot and gray code and so on. So the really basics. There's also an ITE function for ifs and else. This is still needed for VHDL 2008, and VHDL 2019 you can exchange this with a when else construct, which got unified in a way that you can use it everywhere. For older code, you need a function to distinguish inside, let's say, a generic value assignment, which one to assign. We have a collection of data types, lots of them. The most prominent ones are a vector, standard logic vector variant. So it's a vector inside of a vector. And we also have an SLM, which is a standard logic matrix. And with these 2 types, you can be very flexible when it comes to bus interfaces. Okay, we have physical types inside. You know from VHDL, there should be one physical type that's predefined called time. We did specifications for frequency, baud rate, and memory. And with these, you can compute at synthesis time. So at elaboration time, instead of converting everything into times and periods, you can work with frequencies. And when you have an MMCM, you can convert it down to a period. A nice function is a helper called time to cycles. So you specify your clock frequency of the board, the timing you want to achieve, let's say your baud rate, and it's calculating how many clock cycles you need for a counter. It's very abstract, and everything is based on physical times inside of VHDL. As I said, we have synchronizers. We have 1-bit and n-bit synchronizers, flag and strobe synchronizers, and with these 4 plus FIFO that is cross clock, you have all 5 types of synchronizers that exist. In the past, people come to me and say, hey, there's another type of synchronizers. No, it's not. Whatever you bring to me, I can reduce it to 5 types of synchronizers, whatever exists. So some people have special synchronizers, fast to slow and slow to fast. These are just special cases. Whatever you have, you can bring it down to 5 synchronizer types. They are optimized for the MTBF, so we have tried to study the data sheets from vendors and have made special adjustments depending on what the Xilinx is saying, what the Altera is saying, what the Lattice is saying, as far as we could find the data. Then we have at next an on-chip memory abstraction called OC-RAM and OC-ROM with the variants of a single port, simple dual port, and true dual port implementation. You can specify if this is running on distributed RAM, block RAM, ultra RAM, and so on. We can also initialize the memories with files, and it's independent again of the vendor. We have, of course, then, based on these memory implementations, FIFOs, generic FIFOs, then the CDC FIFO. We have a so-called glue or stage. So that's the smallest FIFO you can implement with just 2 stages. And we have temporary put and temporary got FIFOs. So in case you have network transmissions with a retransmission buffer, or you have a CRC check, then you would use one of these 2 types. Next basic module we need is a gearbox. So we have fixed clock rate and related clock rate gearboxes. So in case you need a conversion for 64 bits to 66 bits, there would be usually a gearbox inside of a transceiver. If you need this for other applications directly in your code, we have it also available as VHDL code. For communication protocols, we have then CRC implementations and scramblers, data structures like double-ended queues and stacks, and we have caches inside with a LRU replacement strategy. So what's now missing are arithmetic modules, what everyone I think needs and has, dividers, pseudo-random number generators, conversion between binary and decimal, so BCD, a scalar, so which is multiplying and dividing, and square root and a barrel shifter. And as I said before, for the LRU strategy, we have then sorting networks and sorting implementations. So a LRU is based on some kind of sorting. You can also find an odd-even merge sort implementation, which is fully rolled out in an FPGA. So if you want to utilize your FPGA fully, just take one of these sorting networks, roll it out, and you see how you can use your FPGA completely. If you compare the implementation in here with the book of the author who wrote originally the odd-even merge sort, you find also the fix that is not present in the book. I tried to reach out to the author of the book. Unfortunately, he's not responding. So the C implementation, the C reference implementation is not correct. It's correct with the result, but not with the time complexity, because he's multiple times writing to the same cells, and I found it out in FPGA because I had multiple drivers. It's a nice reference implementation. And then we have statistics. So if you need averages and histograms and minimum and maximum computation, mainly with axis stream data sets running through, we can also do this. OK. For IOs, we have some abstraction layers of the DDR cells inside of FPGAs. Of course, as everyone has it, a UART implementation. I2C, SPI, and MDIO will come with the next releases. We have PMOD modules, some of the tiny ones from Digiland, frequency counters, glitch detectors, PWM, whatever you might need. And finally, we have then an Ethernet stack for IP version 4 and version 6, implementing mainly the UDP protocol. including ICMP and ARP implementation. Okay, what has PLC2 contributed now to this, what was existing there? That's mainly then the AXI infrastructure. So we are talking about packages, AXI FIFOs. Actually, it's more or less a wrapper around the existing FIFOs. In AXI, you have 5 streams. So you put in 5 FIFOs, you connect them accordingly, and then you have your AXI FIFO. We implemented this, of course, then for CDC. We made adapters from AXI 4 to AXI 4 Lite, and we have termination modules, similar for AXI 4 Lite implementations. And here we have then also a generic register. So our idea inside of the PoC-Library is you are having not a code generator. So with an abstract description of your registers, you generate VHDL code, you synthesize it. Because we come from the background using VHDL as its corner cases, we are describing the registers inside of the language and have everything inside of VHDL. So the single source of truth is inside of VHDL. And we can export from there a description in YAML that we can later use then with C compilers and other tools. And of course, there's also AXI stream inside, again, with FIFOs, CDCs, stages, multiplexers, and demultiplexers. Because I'm running a little bit out of time, I'm skipping the AXI register. As I said, our idea is we write everything inside, skipping the register modes, but I want to give you an introduction how it looks like. So the interface is quite simple. You have a clock, a reset. We have a record data structure called M2S, so manager to subordinate from the CPU to the register. There's a reverse channel called S2M, so subordinate to manager. An IRQ line, that's the CPU interface. With VHDL 2019, we can summarize these 3 ports together into one record. And then we have views available, which is also supported by Altera as far as I know. By Vivado, it's supported by the simulators, also by NVC as an open source simulator, and then you can use it everywhere. The output side, we have then the read port and a write port, and we are delivering from within the IP core a hit vector. So whenever software is accessing one of the registers, you get a hit bit, and you see that the register was either read, or in case it's a writable register, you see there was a write update. So you don't need to scan the data. If it has changed, you can directly use the hit bit and use it in the state machine. So going to the description, it looks like this. So we set up a constant with our configuration, which is a register description vector. And then we call our helper functions to AXI for register description. We give it names, addresses, and modes, and then it's defined. We hand it over to our generic description of the register. That's it. Because it's now a constant inside of the language, and let's say you have an IP core that has certain sections that are repeating as registers depending on a generic value, we can call a function, we can call a loop, we can call if statements and case statements and implement more registers, and we can repeat them. So it's quite easy to have a FAN controller with either 6 channels or 12 channels, because you once define a channel, then you abstract this in a function, you call it multiple times, you write all the results into one of these vectors, and it's generated. Okay, what's coming with version 3? What is our plan? Or towards version 3, we released a few days ago the DRP bridge, so AXI Lite to dynamic reconfiguration block when you want to access MMCMs and transceivers inside of Xilinx devices. We have the Git version register based on the register itself. So it's taking your version information, your hashes, your branch names, everything together, compiles it into a read-only register, which also includes the Xilinx DNA port, so we can read out the internal serial number of every FPGA and encodes this as 96 bits of read-only data. We have a high-resolution clock, an adapter to the block RAM, which is called OCRAM adapter, and a UART. The specialty about the UART is we implemented the same interface as a Light UART from AMD, so you can use it with the same software stack and Peta Linux. The advantage is our UART is supporting software and hardware flow control, which is quite nice to have flow control. Okay, skipping this part. As I said, we want to have more and more tests integrated in here. It's very important to not just show our IP cores, but also have some tested documentation updates with reports. So the idea is we are compiling our results directly into the documentation. You find an appendix with all test cases, test results, and it's also an idea to integrate the code coverage from a UCIS database in there. And toolchain support, as I said, more and more tools. And because we have seen many problems in our IP cores, different authors have been active in there. We want to use the step towards version 3 to clean up interfaces. There has been a time where engineers worked on IP cores and said, oh, CLK is a good name, maybe not clock. And then we had engineers starting with data in, changing it to DIN to DI and just to I. I think it's not good for readability because afterwards you have a comment saying data in. So when there's a comment, you can also name it like this. And we want to have a cleanup of all these interfaces to a common style. Maybe not everyone's style, but at least the PoC-Library style. And we want to have a common style inside of our library. And this will be a huge cleanup. And for supporting this, we want to use the VHDL style guide tool. And we have found out you can apply all these different rules. And we want to set up a rule set for us and do this. And last but not least, my last point is with the FPGA conference, we will then provide the multiplexers and demultiplexers for AXI4. And this allows you to implement then crossbars and infrastructure for connecting IP cores together, which are way more efficient and also smaller than the standard IP cores from the libraries, so vendor libraries. So we did measurements, half the size, more frequency, less arbitration loss. Thank you very much. That's my overview on the PoC-Library.
Thank you very much. This library looks very complete, and I'm sure most of us can draw something useful. On this theme, if you visit our website, cern.ch/FBF/FPGA, there is a tab where we list and catalog all of these libraries, such as Pile of Cores, that are somewhat complete, documented, and most importantly, actively maintained. Not as a way to say, oh, you should use this or that tool, but as a way for spare you some effort and have a look of what's out there before you reinvent the wheel. So we encourage you to check this out. And let's open the floor to questions. I see one up there.
Thank you for the talk. So we were also doing register creation manually with VHDL, but then we quickly realized that it's very error prone. If you miss the address, let's say, if you calculate it wrong, everything falls apart. So how do you deal with that problem?
We have internal error checks. So when you set up your addresses and how it's incrementing, so we are checking the modes, we are checking the addresses, that there are no overlaps. You can have different checks inside. That's all done internally. And then it's reporting with a failure. So you have an assertion inside. That's your feedback that you get. The idea is for one of the upcoming, maybe 1 or 2 years, I have seen that Vivado is supporting protected types and synthesis. I did first tests, it's really working. I never thought that any vendor will touch this topic because everyone's saying protected types is just simulation, too complex to implement it. And the idea would be to use protected types to have it better integrated, more checks, easier checks in there. And the, let's say, final goal somehow is to replace a block design, because then we can have automatic memory allocation and interrupt assignments and so on with protected types. So every IP core, let's say implementing such a register interface, is trying to connect to the protected type instance in your design and says, hey, I need 64 kilobytes of memory and 2 interrupt lines. Where do I need to go to the bus?
But then it will be very tool type specific, right? Because maybe Vivado will do it differently than the other
So
guys.
tool time, yes, currently it's slow. 26.1 should be way faster. They had an internal thing.
All right, thank you.
Okay, I saw 2 other questions. I think one down here first.
Hello. So, thank you for the nice presentation. You mentioned about the CI/CD. So do you also test on the CI for different vendors? If yes, is this also open source? And do you use like some kind of a Docker? And what kind of operating system do you use for that?
So inside of PLC2, we have our internal PoC-Library variant, which is running with CI/CD. So there we are running a synthesis test with Vivado. We are running Revera, GHDL, and NVC. Outside on GitHub, I only have GHDL and NVC. I have no access to commercial license. And the bigger problem is where to store the 170 gigabytes of a Docker container. That's a bit of a problem. Internally, we have a special setup with GitLab runners, GitLab CI. And I'm not sharing Docker containers. We have a different technique. We can talk about this outside if you want to know more about this, how to efficiently implement CI/CD when you have around 23 different versions of one tool, and it's then usually taking terabytes of space. And we figured out that you can hard link all of them together, and then one change to another version is not so big. And you can see when Silicon Valley was active and not active.
So also, my question was regarding, so if you use Linux, like everyone might know now that next version, the AMD has decided that Vivado is not going to support Linux, unfortunately, for the free version.
I want to ask at Silica, is this really true? What they have written on the website that they're ditching Linux support for the free version? We have to figure out, or write a LinkedIn post and get a new contact. I don't know. Let's see.
Thank you.
I thought there was another question up there.
Yes. Hi. Thanks for the talk. Also regarding the AXI library for registers, I mean, there's a community effort to have libraries that automatically, generate the RTL code based on the description base, like YAML files, for example, for registers, so that both software and hardware developers have a single point of truth about what the code is. What do you see as the advantages of using this type? Because we also use something similar, but then all the information is within HDL files. Then this other approach seems to be more. It seems to bridge a little bit the development between software and hardware developers.
So our understanding is we are writing the design. We design the hardware. We are in control of the registers. That's why it's inside of our well-known language. You can have other opinions to say, hey, I come more from the software world. I want to generate it. We have seen in the past problems when you have generated files that especially tools like Vivado say the file has been updated or is outdated. I need to resynthesize even if you didn't touch it just because on the timestamp. So we are avoiding this. That's one of them. By having the names and everything inside, and we are generating from their YAML description. And from this, we can generate then C structs. So the idea is to deliver C structs directly to the compiler for embedded software development. The hardware engineer is free to optimize the hardware. So you can move around registers as long as they are still existing and you're not renaming them. You will get a certain kind of freedom to move registers around, to have debug registers, to throw them out. Otherwise, I have seen in the past when you have more this generating approach, registers stuck forever in your design. You never get rid of them because software is not updating. So what I can do, I can change it. Then the C struct is changing. If it's the same code, the software designer will not notice. And if I have changed it, then the C compiler is crashing and says, hey, this thing doesn't exist anymore. You need to update. That's a smart hint of read the documentation again and come to our meetings and see the register changes.
But then maybe I misunderstood, but in your library, all this information is on the HDL itself, right?
So the description is inside of VHDL.
Exactly, so it doesn't use any external YAML, TOML, or anything, right?
So when you instantiate it, we are writing, so we have a helper function that is assigning to a dummy Boolean variable to call a function, and this is in the background writing into your synthesis output register, output directory. It's writing then files, and this can be picked up by the compiler.
But there's no generation of C headers or anything based on that. There's also?
So we have a post-processing where a Python script is taking this and converting this to the C headers.
Okay, thank you.
Switch over to this side. I think Francesco had a question.
So I had a look on the website, and what you recommend to use the libraries to include the whole repository as a submodule. which is a good thing because then if you publish updates, then but the back, like if you do that, you have also some disadvantages, like you include everything, even if maybe I just want to use a FIFO. And then a second question on this is, a FIFO is going to be made of few files, maybe, or several files. So how is the inclusion of a specific core from the pile done? And this is a question that I'm asking with the hat of a hog developer.
Okay. So for the usage, the main usage idea is to use it as a submodule. I would say that's the most efficient one because then you can get updates and so on. There's also a description on the help pages saying you can still download the zip file, then you have it as it is. You can have a normal Git repository and link from your project to it, but if you have multiple projects, you update the PoC-Library, it's updating everywhere, maybe not so good. That's why we propose to use a submodule. Also for contributing into the project and uploading this either to GitHub, or if it's company internal, you can also like clone it into your company. From there, you are using this as a submodule. You can have company internal modifications. That's also a nice benefit of having a submodule. When it comes to integrating this into Vivado itself, EDA Square will take care of it. So we have a description currently for OSVVM with profiles. And I made a tool which is called EDA Square OSVVM that can read OSVVM's profiles with enhancements for synthesis and timing constraints. So you have a full description of your design. And you can ask for sub-portion of it, including design hierarchy and dependency scanning. And it gives you then a list of commands for Tickle to insert into your Vivado for loading the needed files. And the idea is to automate it even further, that you just call this functions, helper functions, say, hey, I want to have the FIFO inside. It's checking which files are already existing and what is needed on top of it, depending on the dependency graph.
Okay, thank you.
But we can talk about how to exchange knowledge with tooling around it.
Okay, I thought, there was a question here in the middle.
Yeah, thanks for the nice overview. You mentioned compatibility issues between VHDL 2008 and various Vivado versions. Do you happen to maintain a sort of compatibility chart or like documentation on which version of your course works with which version of Vivado?
Not directly openly. If you go through the code or you have it checked out as a Git repository, just grab for a workaround. And every workaround that's inside of the tool, we are writing down what tool it was, what version it was, and so on. So when we come back a year later, we can check if it's maybe fixed, if it's gone, and so on. And you find a nice summary of what happened in the past 10 years with certain tools.
Okay, thank you.
Any other questions?
Or come directly to me, and we just talk a little bit, maybe 1 hour, 2.
Yeah, indeed, we will find Patrick at the stand as well. If there's nothing else, okay. Maybe last one up there.
I was wondering how you convince your company to open source all of this.
So first convincing point was to use it internally. There have been lots of fights because when you are, especially as PLC2, tied to AMD, it's always you can have these ticket systems, you can call them directly, and they're responsible for IP cores, so you're not blamed by your customer, which is okay somehow in the world of contracting work. The problem I saw is when they fix the problem, and you tell your customer it's now fixed, the customer comes back and says, why have you not implemented this in 1 day? But you need also 2 weeks to react to it. So now you have a fix or some modification. How can you adjust to it? And I would like to take this time of waiting 1 week, 2 weeks that AMD, whoever it is, takes to respond, plus the 2 weeks I need either way, and maybe I'm faster because I have written the code, I can look into it, I can simulate it, I can fix it. We have seen problems inside of, let's say, the data mover. So when you have not aligned data in your data words and you use the strobe bits at the end, or the strobe bits? Yeah, strobe bits at the end, and you don't have always full words, it's not counting correctly. We cannot fix it. So we needed now to instruct our software guys and say, hey, always have fully aligned data transfers. You cannot have ragged ends, and we cannot fix it. And the goal is internally, we have DMAs, we have a special DMA with aligning data in memory for multiple channels to write our own data mover to get rid of this restriction. Yeah? This gives you freedom. And we have seen in the past that having these open source IP cores, we are way more efficient. Everyone in the company knows how to use them. So we have now trained our internal staff. That's very good. And we have also proven by replacing existing IP cores, let's say this AXI stuff, inside of block designs, we reduce it by 30%. That's a lot what you gain, yeah? Just by using your own FIFOs and converters. So it's way more efficient.
Okay, I suggest we thank Patrick again.